we've already talked about the main ideas you're going to see in section 4.3. Take one of those ideas, and we talked about the tangent planes, how you get two vectors, tangent to surface, take the cross product, you get the normal and all that stuff. Okay. So we talked briefly about that, but let's go ahead and do some examples. Now, the overview is, if you got pause per second. Okay, sorry. Something's going on with the camera here. Things are crooked. Had to make a couple adjustments. I'm gonna have to play with it a little more than that a little bit later. Um, okay, let's say we got a function f of x, y. Then kind of summarize what we've already said. Fx of xy is slope in the x direction. Now, I'm not being real specific. I could say fx evaluated at a specific point, x naught, y naught, is the slope, instantaneous slope, if you move in the x direction from point x naught, y naught. Okay? But I'm not going to get that specific. You understand that it's a slope in the x direction. If you understand the pictures we did last time, which you probably ought to review if you don't, or look at the pictures in your book. Imagine what the pictures in your book would look like if they were the picture I made. Look a lot better than the one I made, but I think the one I made was maybe clear. Fx is a slope in the x direction, so I plus fxk is in the direction of the tangent. At a point. Similarly, J plus Fyk is in the direction is in the direction of a tangent vector at the same point and all that. And you can look at how that's stated very explicitly in your textbook with all the conditions and everything. Okay. That's the idea. You got this vector and this vector. Therefore, I plus fxk crossed with J plus Fyk is normal to the tangent plane because you got a vector that's tangent in the x direction, you got a vector tangent in the y direction. Cross product of those two vectors is going to be normal to the tangent plane. Okay. Well, What's that cross product? You could use a determinate definition if you want to fall back on it, but it's pretty easy since you've only got two components here. I cross J is K. I cross K is negative J. K cross J is negative I. So your cross product, I cross I is K, I cross FYK is negative FYJ, FXK cross J is negative FXI, and FXK cross FYK is zero because K is parallel to itself. The cross product is zero. Sine of that angle, two parallel vectors is 0 degrees, sine of 0, 0, right? Putting these in the order X, Y, Z, or IJK, it's negative FXI minus FYJ plus K. If you want your unit normal, and you don't really need it to get the equation of the tangent plane, but there are times when you might want the unit normal. It's just negative FXI minus FYJ plus K over the square root of 1 plus FX squared plus FY squared. And that should be obvious. Pythagorean theorem, basically. Okay. So at the point, now I'm going to get specific, at the point X naught, Y naught, and what's the Z coordinate? It's F of X naught, Y naught. The tangent plane, and I'm going back to the reason the tangent plane is what it is. It's characterized by the fact that the vector, this is the vector X naught, Y naught, F of X naught, Y naught, to the arbitrary point X, Y, Z. Okay, because the vector from one point to the next, you just subtract the X coordinates, you find the change in X, that's times I, change in Y times J, change in Z times K. And that's exactly what I've written down, X minus X naught I plus Y minus Y naught J plus Z minus F of X naught Y minus can't talk, times K, okay? That's just the vector from here to here. So it's X naught, Y naught, Z naught here. X, Y, Z here. Instead of Z naught, I write F of X naught, Y naught. Okay, so I've just labeled a point, F of X naught, Y naught, F of X naught, Y naught, F of X naught, Y naught. And I've labeled another point, X, Y, Z. And here's the vector. Okay. And then here's your normal vector. And from whatever perspective you happen to be viewing this, there's a right angle. I mean, if there's a right angle between the vector from X naught, Y naught, and so forth to X, Y, Z, if that vector is perpendicular to the normal vector, the point's on the plane. And only if this vector is perpendicular to the normal vector is this point on the plane. And I'm still not seeing the entire picture. There it is. Okay. So you should, one thing I keep seeing on your homework, which looks pretty good. Okay. I don't see any pictures, or very few, unless you're actively asked to sketch a picture of this surface or something like this. I'm not seeing any pictures, so I'm not seeing any graphical thinking. You might be doing it, but you really ought to be writing it out. I'm not going to penalize it. I'm just saying you're going to retain it better and do better on a test if you get in the habit of drawing pictures and doing a little expanded explanation. You'll retain it better. You'll understand it better. So just advice. I'm a little uncomfortable that I'm not seeing more pictures, deeper explanation. I know you're in a hurry, so you write down what you write down. And if you understand it, fine. It'd be better off if you take just a little bit of time and sketch, even if they're bad pictures. I'd rather see a bad picture than no picture. Okay? If I see a bad picture, then I can comment on it. I won't penalize it unless I'm asking for a picture. Okay. So there we got it. Okay, we've got this vector. It's characterized by this vector perpendicular to the normal vector. So I've just rewritten the vector x minus x naught I plus y minus y naught j plus z minus z naught k. Put big parentheses around that. Cross product of that with negative fxi minus fyj plus k equals 0. Now I could actually write the result down here, but it'd be so close to the bottom of the board, I'm afraid the camera will pick it off, won't pick it up. And Zoom has this thing across the bottom of the screen I can't do anything about, so I can't tell for sure. So I'm going to come up here and say that this whole cross product here is just fx times x minus x naught negative minus fy times y minus y naught plus z minus f of x naught y naught equals 0. That's the equation of your tangent plane. Let's do an example. Let's let f of xy equal x squared y plus y cubed x squared. Find the tangent plane at the point 1, 1, 2. Spring is sort of hitting me, so I'm keeping the numbers as simple as I can. Okay. Each term is one because each variable is one, right? Just raised to the power, no coefficients. And then when we add 1 and 1, we get 2. So the point 1, 1, 2 lies on the graph of this function. And that hopefully is obvious. Okay, the normal is going to be n equal negative fxi minus fyj, should have been minus, plus k. Perpendicular to x minus 1i plus y minus 1j plus z minus 2. Okay. Now what's this vector? This is a vector from 1, 1, 2 to x, y, z. Okay. Same vector that I said here, vector from x naught, y naught, f of x naught, y naught to x, y, z. So that should be intuitive or should become intuitive as you think through these things. If you just do this by following formulas without thinking about what they mean and thinking about the geometry, it's going to get away from you real easy. Unless you're really, really good with formulas, and some people are. Okay. So, but don't count on it. Well, we've already seen what happens. We take the cross product. I said cross product. It's another piece of evidence. You should never believe anything I say until I've said it twice. We use the cross product to get the normal vector. So I had cross product in my mind, but if the vectors are perpendicular, their dot product is zero, not their cross product. And it's the dot product that gives you the equation that I just wrote down. Okay. So I apologize if I misled you. It might take you years to get over the trauma, but work on it. Okay. So we take the dot product of these. Dot product is zero. Thus, x minus 1 I'm going to have room to get all this in, but I'll probably erase something. Fx times x minus 1 negative fx minus fy times y minus 1 plus z minus 2 equals 0. Now, what are we going to do about fx, fy, and, well, we just need to know what fx and fy are. Where do we need to know fx and fy? At the point 1, 1, 2, because that's where these things are tangent. Okay, that's where the vector 1 plus fx I plus fxk, j plus fyk. That's where those vectors live. Okay, that's where those vectors are tangent to this plane. Okay, so what's fx? Fx is 2xy, right? Plus 2xy cubed. X and y are both 1, makes it easy. You get 2 plus 2, which is 4. Okay, I'll write that off to the side just in case. You get negative 4 times x minus 1. Then it's minus fy. What's fy? Well, it's going to be x squared, and then it's going to be 3y squared x squared. So you got to get 1 and 3. You're going to get 4 again. Didn't mean to make that happen, but it happened. Okay, so it's going to be minus 4 times y minus 1 plus z minus 2 equals 0. So there's the equation that ought to represent tangent plane to the function f of x y equals x squared y plus y cubed x squared at the point 1, 1, 2. Now, I'll pull this over so you can see it. And I actually want to clean this board real quick so we can use it. Just to fill in that last little detail, fx of 1, 1 equals 4 because fx equals 2xy plus 2y cubed x. X and y are both 1, so you get 2 plus 2, which is 4. And fy of 1, 1, I think equals 4 because fy equals x squared plus 3y squared x squared. Again, x and y are both 1, so you get 4. So that's the reason for the negative 4s in the equation. Okay. Now, the point I want to make is that near the point 1, 1, the value of the function is close to what you would get on the tangent plane. So I'm going to just say okay, again, the plane is negative 4 times x minus 1, negative 4 times y minus 1, plus z minus 2 equals 0. We can solve that for z very easily. Let's see, we're going to get plus 4 here, and plus 4 here is 8. 8 minus 2 is 6. So z equals something minus 6. And the other something is 4x plus 4y. So that if x equals 6 and if x equals 1 and y equals 1, we get z equals 4 plus 4 minus 6, which is 2. Okay? That's a point 1, 1, 2, which is the point we originally chose. Okay? So we know that 1, 1, 2, the point 1, 1, 2 is on the plane, and it darn well better be, right? Because our whole hypothesis is we're finding the equation of a plane tangent to this surface at that point. Okay, so the point has to be there. Now, z is this. You see, if x equals 1.1 and y equals 0.8, what's the point on the plane? Well, we plug 1.1 in for x, right? Then we're going to get 4.4 instead of 4. Plug in 0.8 for y, and we're going to get 3.2 instead of 4. Means we're going to be 0.4 units less than we would be at 112. So I think that puts us at 1.1, 0.8, 1.6. How do I get that? I just plugged 1.1 in for x, 0.8 in for y. And that's what I got. I got 4.4 plus 3.2, which is 7.6, minus 6. 7.6 minus 6 is 1.6. That's not actually how I calculated it. I calculated it by saying that this number is going to become 0.4 more. If I do 1.1 instead of 1, I'm going to get 4.4 instead of 4. So this one goes up by 0.4, and this one goes down by 0.8 because my x is changed by plus 0.1. 4x is going to change by 4 times 0.1, which is 4. It's linear, in other words. Y is going to change. Y is changed by negative 0.2. Okay, so 4y is going to change by negative 0.8. So my next change, net change, is going to be plus 0.4 minus 0.8, which is minus 0.4. So instead of getting 2 as I would on the actual function, I'm getting 1.6. You should understand all that, but I'm going to kind of bring it out a little bit. The actual function, f of 112, let's make sure it's x squared y plus y cubed x squared, right? Take a peek and make sure I've got it right. Okay. So x squared y, 1.1 squared is 1.21. I multiply that by 0.8 and I get 0.968, I think. And then it's plus y cubed, and y cubed is 0.512 x, which is 1.1, and 0.512 times 1.1 is 0.56, and I'm losing it 1, 2, 512, and 0.562, and then I'm guessing it's something like that. Okay? Did you get it? Somebody calculate on the calculator? I'm not sure about these numbers, but that's going to come out 1.54, I think. I had those numbers. Now, you take your calculator, figure them out, see if I did it right. I think I probably have one of the significant figures wrong because my working memory's shot. It's about average today, so it's just on a good day, it would be just a little clearer. My point is then, the tangent plane approximation is 1.6. okay? What we get from the actual function is 1.54. This function is not a linear function, right? It's not linear in X, it's not linear in Y. In other words, it's not a plane, okay? Got some curvature. So between the point all kinds of stuff down that I shouldn't. I said 1, 1, 2, because that's what I've been doing. Let's make the statement correct. The actual function f of 1.1, 0.8, you can't even do the function f at 1, 1, 2. 1, 1, 2 is a point on this graph, okay? So just kind of ignorant to write that down. Can you read that? Let me rewrite it one more time. The wet spot on this. Okay, f of 1.1, 0.8. If I did my arithmetic correctly, comes out 1.54. If I didn't, you can correct it, but I'm not far off. So that our tangent line is at 1.6. Our tangent line is above the actual surface. Okay. At the point 1, 1, 2, where x is 1 and y is 1, our surface is 1.6 units above the xy plane. Our tangent plane is 1.6 units above. Okay. And the actual value of the function is 1.54. There's something else I didn't write correctly. And let's try to clarify what I'm really saying. Comparing a function gives you 1.54, tangent plane gives you 1.60. So just I don't even need axes. They wouldn't hurt, but who knows where they are, okay? So here is, let's say the point 1, 1. Writing things down without thinking. 1.1. Here's a point 1.1, 0.8, 1.54. And here's the point not in this direction, so be it. Here's the point what I'm doing would be reasonable, but let's do it right. Okay, down here in the XY plane, got the line X equals 1.1, the line Y equals 0.8. And I've got them crossing at what looks like the Z-axis, which is a bad idea, but we'll just live with it. Okay. So here's the point. One point 0.8 in the XY plane. On the tangent plane, you get on the tangent plane, you get 1.1, 0.8, 1.6 lies 1.6 units above the point 1.1, 0.8 in the XY plane. Arrow or vertical line is 1.6 units long. The actual function something like 1.1, 0.8, 1.54. Now I've got the arrow for the tangent line, the arrow from 1.1, 0.8 in the XY plane up to the tangent plane is orange. The arrow from that same point up to the actual function is in blue. And I've got them offset slightly so they don't necessarily look like they're coming from the same point, but they are. And what you're seeing then is, again, the tangent plane's a little bit higher than the actual function. Whereas at the point 1, 1, 2, they're identical. So let's just say the point 1, 1, 2 I don't have a good way to draw it here, but let's say the point 1, 1, 2 is I'm going to try to draw it. Here's a point 1.1, 0.8, 1.6. Here, directly below it, is the point 1.1, 0.8, 1.54. It's 0.06 units below. This is on the actual graph. This is on the tangent plane. This is the actual surface. A point on the actual surface. This is a point on the tangent plane. Point 1, 1, 2 is a little higher than either of these. It's a little to the left as the x-axis has gone left and right, and a little bit in front of any of these points, and a good bit higher. So I'm just going to say it's here. And this is a point on both the tangent plane and the actual surface. Does that make sense? Everything is flat and linear from here to here. The tangent plane is just flat from this point on the actual graph over to here. So I'm going to just indicate that by saying, well, everything's nice and linear from here to here. Now it's linear in 3 dimensions. So it means there's a normal curve and all that stuff, okay? Or normal vector. From here to here, the plane itself it's not curved the way I've drawn it. Almost certainly not. Okay. Between these 2 points. It's not curved very much between here and here, but it's curved so it doesn't match the tangent plane. The big idea is the closer I am to the point 1, 1, 2, the less difference there tends to be between the surface and the tangent plane, less distance. Okay? So I'm just going to make the statement that close to 1, 1, f of x, y is close to the tangent plane approximation. Gotta adjust this thing so stuff stops falling off of it or put a lip on it. Okay, well, that's the idea of the tangent plane. That's a big idea. Okay, one of the big ideas we want to understand this week. And that's really mostly what section 4.4 is about. Now, there's this thing called the total differential, which makes this even easier or makes your understanding more complete. So we have f of x, y equal x squared y plus y cubed x squared. Partial f with respect to x is 2xy plus 2y squared x squared. Partial f with respect to y is x squared plus 3y squared x squared. And let's see, this should be 2y cubed x. Not sure what I was thinking when I wrote that down. I was thinking it had Okay, f of x plus delta x y is f of x y plus fx delta x. So I'm going to call this fx. I'm going to call the x derivative of x fx. I'm going to call the y derivative fy. And f of x y plus delta y equals f of x y plus fy delta y. F of x plus delta x y plus delta y equals okay, when I say it equals f of x y plus fxx in the first case, I'm going to use a capital E for an error term, okay? Because this assumes the function is linear between x, y, and x plus delta xy, okay? And it's not linear. Function's not linear in any direction. And then I'll say, yeah, there's a plus E here. And this E is not the same as this E. E just says there's some error. And the error gets bigger as delta X or delta Y, or both of them get bigger. Okay? A small error if delta X is small because you're close to the point and you're not far from f of x, y. Okay. So f of x plus delta x, y plus delta y equals f of x, y plus fx delta x plus fy delta y. In other words, fx tells you how quickly you're changing with respect to x. You multiply that by how much x changes, and you get how much this thing ought to change if the rate of change doesn't change. There's no curvature. There is curvature, so there's an error term. Similarly with fy. Now, differential is often written fx dx plus fy dy, where dx really means a delta x, some change in x, and dy is some change in y. Okay? And this approximates change in f when x changes by dx and y changes by dy. It's closely related to the tangent plane because this would be the change in our example where x changed by 0.1 and y changed by negative 0.2. Make sure I don't write the wrong function. Did I write it? I think it was x squared plus y x cubed. If x is this, fy is this. At the point 1, 1, fx equals 4, fy equals 4. So relative to 1, 1, df is fx is 4 dx plus 4 dy. If dx equals 0.1, y equals negative 0.2, and what do those numbers have to do with the example we're working on? Well, you're moving from 1, 1 to 1.1, 0.8. X changes by 0.1, Y changes by negative 0.02. So this is bringing us back into the context of what we've been working on all along. dx equals this, dy equals this. So df equals 4 times 0.1 plus 4 times negative 0.2 equals negative 0.4. And you see where those numbers came in, everything we just calculated. We go from the point 1, 1, 2 to the point 1, 1, 1.6, because df, the change in our function, is negative 0.4. And the value of our function started at 2 and went down to 1.6. We didn't even have to do a tangent plane in order to do this, but the tangent plane is important. Okay. But this is really just equivalent to what we get from the tangent plane. And if you sort that out and pull all that together, it's a really good chunk of stuff to know. Okay. It's a really important insight that we build on several times during the rest of the course. Okay. So I probably held you a couple minutes. Yeah. Now we're only 3 minutes over. So on a snow day, but I know you got places to be. So we'll stop there and then pick up. I recommend you scan ahead in sections 4, 5, and 4, 6. Because both of those will be assigned for next time. But for now, I ask you to do 4.4.